Stephen Wehner and I run the Bugmaster Institute here in Vancouver. Today I have a video about the STFT for you, the short-time Fourier transform. If you follow online discussions about audio processing, in particular relating to machine learning and AI, you will likely find people talking about the STFT. You may have looked up and learned the math. Where does it come from? How does it work? What is the input? What is the output? And how can it be used? You can find a lot of good introductions to the theory here on YouTube and elsewhere on the internet. But here I want to show you in a hands-on way what it's all about. It took me a while, but now I have completed 3 Jupyter Notebooks demonstrating the STFT in simple cases. I have put these on GitHub so you can download them and run them yourself. They may also be useful to start new projects, just as a basis. So in this video, I'm going to go through them with you, explain the steps, and add a few pointers here and there. But before we start, just a few words about the STFT. There's a way to look at the fast Fourier transform that it pretends your function, your signal, is periodic. There's no time as such in the output, just amplitudes for the different frequencies. Whereas the STFT, the short-time Fourier transform, is for finite signals. You have some sound starting at some time and ending at another time. There's no repeating. There are amplitudes for the different frequencies, like with the FFT, but the same frequency gets amplitudes at the different times. So the STFT gives you a mathematical method to obtain such an evolution over time. This sounds great, however, it is not quite as mathematical as the FFT. This is because there are a lot of choices, a lot of parameters, as you will see. I like to say the STFT is not as absolute, because someone else may come up with different results, even when they work from the same signal. But let's start up here. So this is my bash console. Let's make the font a bit bigger for you. This is the GitHub URL, stefan-bugmaster/stftdemos.git. What do we have? We have a few files. We have a sample var file. We have a readme. We have 4 Jupyter Notebooks. This one is sort of a bonus. We have the requirements.txt and we have the pip install log. I should have left out the pip install log. Let's look at the readme. So we have instructions how to get this running. Source and install the requirements. This will take a while. Look at the README again. So we're at the last step. We can start our notebook. Our notebook server, and that will also bring the browser window up. Okay, so now I will open up my browser and we'll go through the first notebook. Alright, here's our first notebook, STFT Demo 1. We're first going to read in a WAR file, which comes with the GitHub repo, mlkintro.war, which I got from the archive.org. It has the standard 44.1 kilohertz for the sample rate. The array, the numerical array has 174,722 values, and it's stereo. And it's a NumPy array. We can listen to this by using this IPython package.
I am happy to join with you today.
A very recognizable voice, if you ask me. I can show you the usual plot of this signal. So the left and right channel, what I call bubble plot, So we say we have about 4 seconds of recording here. For the STFT, we want a single dimensional array of numbers, not twice. So this is a simple way to collapse the two channels. You could also use one or the other. But for the sample here, we just do a simple thing. So finally, we come to the invocation of the STFT function, which we got from the SciPy implementation. So what are the inputs? We have the signal, of course. I've chosen this window function. Fs is the sample rate. So the number you choose here basically tells you, it makes it so your return values are in natural units, so to speak. So the sample rate is 44,100. So basically every 44,100 values you have a second go by. And so that will be reflected in the way these numbers come out. You'll see that later too. NFFT is the number of Fourier frequencies, but also the number of Fourier coefficients that you want to be computed. I chose this as a sample value. And n per sec is how long is a segment. And I chose this value here, 500. You can find the full documentation at this link. Let's run this. It doesn't take very long. And so what did we get back? We got back 3 arrays. We got back 3 NumPy arrays. The first one is the frequencies, the second one is the times, and the third one is the actual complex Fourier coefficients, and it's a double indexed array, as we can see here. So we have 7,351 frequencies, we have 700 times, and our z-axis is indexed at these frequencies and times. So for every time, we have 7,351 different Fourier coefficients for each of these different frequencies. How do these values come about? So the 7,350 comes because we ask for a sample rate divided by 3 many Fourier coefficients. And so then we divide that by 2 again because our z-axis is, they are complex. So that's two dimension. For the times, we ask for 500 segments of width 500. And so 700 times 500 comes to about just the length of our input. We have a discrepancy because of padding that needs to be done when you do work with the FFT. Let's look at the values first of the frequencies. So we have because we divided by 3 here, our frequencies are spaced by 3 as well. For the times, we have, so remember, we have our input signal is, the length is 3.97 seconds. And so we have 700 of values. Our time interval of 3.97 is divided into 700. And so that comes to 0.00567. And that's just about our spacing of the different times in our times array. All right, so let's look at the main point of the exercise, the z-axis array. So I chose, as a sample, I chose time at 250, which is 1.42 about. So if you look above in our plot at 1.4, we have some signal going on. And you can see the z-axis is complex valued. You have your j here. And this is what the spectrum looks like at this time 1.4172. You see there is some structure to this. I cut it off at around 6 kilohertz because, it flattens out. We can look at the evolution further down. So the next two plots look like this. So you see there's change over time. And we can also look at the usual color mesh, sort of a plot where the amplitude is color coded. This takes a bit of time to compute. Okay, so that was about a minute or so. Yeah, so this, I'm sure you've seen this before. Basically, we have the time, and we have for each frequency we have color coded amplitudes, and again we plotted the absolute value of the coefficients. All right. So one other thing I wanted to mention is that we can invert the value of the STFT. So the STFT operation can be inverted. So you could change the ZXX array. You could add something to it. You could remove something. You could remove some values, and so then you could get, by using the ISTFT function, you can invert. You can get the signal back. So let's run this. This also doesn't take very long. So it's just a array of one dimension, and about the length of it just as expected, and it sounds like this.
I am happy to join with you today.
In the first notebook, we used a real-life audio signal, speech recording. Now we look at our artificial audio signals, so we have an idea what to compare the output of the STFT against. Our second notebook, STFT Demo 2, we're going to import the usual packages. So this is how we're going to make the artificial signal. We're going to have a sine wave, and the frequency will be time dependent. We're going to work on 1 second of signal. We're going to use a moderate sample rate just to have some variation. So our frequency will depend on time by starting at 440 Hertz, the standard A note, and we're going to increase it linearly over time. So over 1 second it'll go up. And the way this works out, it's going to go up from 440 Hertz to 540 Hertz at the end. Let's run this. So we have 10,000 values in our signal. The signal cannot be plotted because it alternates too quickly. If we plot a smaller subsegment, we see the alternating values. We know that they alternate at a faster and faster rate, but we cannot see it here. We can hear it. So I'm going to play this here. It's going to play it 3 times, according to the tiling here. So that's your pure sine wave with increasing frequencies. We can look at the FFT. So this is probably worth its own video. Why does it look like this? However, for now, I think it's fair to say this is not really what we're after when we want to understand this kind of signal. We want to see the frequency going up linearly over time. So here we invoke the STFT. Very standard, no special arguments here. We have 1,000 values per segment, so we're going to have about 20 segments. Here we are. We have 5,000 frequencies and 21 segments. We can look at the spectrum at the initial times. So we see that it is close. The peak is close to 440 hertz, and it is pretty much spread out. So it's not, it's not giving us a exact 440 hertz. It's giving us a kind of 440 hertz. And we can go to the intermediate time. So at time 10, we get this picture. Our peak frequency has moved up to about 480 hertz. And we can look at the end of the analysis. We are close to 500 hertz here. If we go to the last entry, we get it breaking down. So it's not quite the same shape. And here we have the whole collection. So we see how we started around 440 and we got to around 540. In the next notebook, we'll make our input signal a bit more interesting, and we'll also add a simple analysis of the output of the STFT. Okay, our third notebook, STFT Demo 3. We're going to import the usual packages. So here I have made a signal which is composed of two nodes. The first node for the first half of the second, and the second node for the rest of the half of the second. So yeah, we have a signal of 1 second length. We have the first node has a frequency component of 400 Hertz and 800 Hertz, and the second node has 600 Hertz and 1200 Hertz. However, both of these nodes have increasing frequencies, like with the method we had in the second notebook. So we're gonna see how this sounds in a moment. But I forgot, yeah. So we have an amplitude of 1.2 for the first part and just 1 for the second part for each node. You can see that when we plot these, of course, it doesn't look like anything we can really relate to, but we can sort of understand the way it sounds. So hopefully you could hear there are two notes at the same time, and both are going up. When we look at the FFT again, it looks interesting. We can look at the STFT. So the parameters are very simple here again. We get 20,000 frequencies. So here I have a sample rate that is higher in the second notebook. We have 80 time segments. And when we plot this, the absolute value again, we see two peaks at, the earliest times. Two peaks and with different amplitudes. We can go to the half of the transition. We see two peaks at slightly higher frequencies. And at the end, we see how the two peaks march in parallel, so to speak. And now I want to add some little analysis to this. So we're going to use a SciPy function called find peaks. So it's going to give us the index of the peaks in this signal. It's not particularly, I don't find it particularly easy to use. You have to sort of work with the kind of signal that you have and, for example, look for suitable values to compute these, to get a useful result of peaks. So this is the result, the peaks that come from this function. Has prominences and all kinds of extra information. We're going to extract what we find useful, and that is we're going to take the first value from each peak, and that is going to be an array. That is going to be an array itself, and that array might have 2 values or only 1 value here. If we plot the first value of these arrays, we get the frequency that is increasing over time, and then it jumps to the other value as we constructed our signal. Well, I hope you liked all of that. I will make some shortcuts, one for each notebook at least, and leave them in the description of this video. Thanks for watching.